can give you now my last lecture about everything what you heard about. And before I start, I want to point out some interesting news which I picked up just by flying to here. That's the theory out of Africa. And the old theory was that Neanderthal people and the Homo sapiens more or less evolved by the same route, coming out from Africa, Central Africa, over basically here Israel, Egypt, Israel, and then diverting to Europe and then to Asia. But what they found out by excavations in Israel, that lots of Neanderthal were living there, so more or less they blocked the view of Homo sapiens. So what they think now is one move of the Homo sapiens was blocked here, and the other ones just went over Arabia, and look where they ended up, just in India. So we are much more related what we ever thought, the Europeans and the whites, and they think that that happened about 40,000 years ago, that within 8,000 to 9,000 years they moved up to here. What happens in the other direction, we don't know, but at least you can say you're really the ancestor of the European race, according to knowledge what we have today. Okay, so that's the news, what I picked out of this Swiss journal. And now you have seen we put up our software system, and I tried to show you a little bit what we can do. This is the so-called Basel package. We called it Bayesian sampling, environment and language. And the reason was because when Gelfand visited Basel, he said B plus S is L. And he said Bayes plus simulation is life. And I said, well, if you just plug in here and equals, then you have Basel. That's the Basel package we want to do. So we started doing this in Unix, and now the PC version is available, and we brought one of the copies, and that's the PC version 1.0. It's not the full-blown version because we found out that it's difficult to link the same Fortran programs to the S Plus system. It's running always under S Plus, and you can use the old S Plus version to do this. But the Fortran compiler under Unix and PC seems not to be the same, so we get some problems in some of our modules to calculate marginal likelihoods, basically what we have done, but then we go on to GIP sampling, and I want to explain to you that briefly. So this is my co-workers who do lots of this programming, because it's really difficult to keep up with this, and we are doing this now in the last 2 to 4 years, and I hope we can do a little bit of this what I showed you in the last years, lectures, and also for the multi-rate case, which I couldn't go too much into so far. Well, just as a reminder, we have done some of the univariate models, and we have a choice of fractional priors, sometimes non-informative priors or partial non-informative, and then the full informative prior. We haven't done all the Cauchy priors, which Professor Ghosh was talking about, but that would be a nice possibility. So remember that for a regression model like this, the fractional prior comes always, or the fractional marginal likelihoods, which is written here, is calculated on the concept of fractional prior, which is implied by this fractional base factor, which Tony O'Hagan developed. And similar things can be done for the intrinsic base factor. That was Professor Ghosh was talking about, the work of Berger and Ricci and other people, but there are more, the diversity of intrinsic base factors is larger than the fractional base factor at the moment, so we stick with this, and then we find out what to do next. So those are the explanation of the manuals, which can be downloaded, and from the web as well, but I brought a copy, and Mohan has it, and so you can do this. So we describe here what the data are, and each of the module comes with an implied data set, so you should check if the results are the same as we have here in the manual. And ML stands for marginal likelihood, and FER for fractional prior. And this is the module, and it's invoked by the three commands here, or four: data Y, MX, the order, data X, the data matrix, and all the stuff is explained here. And B is the fractional parameter, the fraction of your sample, which is used to calculate this fractional prior, and the default parameter is 1 over t, and this gives always the basic or the most simple solution. So the model we are using here is related to the idea of capital asset pricing models, and what we have done is view the world, the continental stock exchanges as some kind of portfolio where you want to invest, America, Chicago, or in Europe, or in Asia, and there we have the smallest portfolio possible. So we have this MSCI indices for Asia, Europe and US, and the world index, and then we find out by the relative behavior to the world index if you should invest more in Asia, as it was very profitable in the last half year. Everybody knows. Why should you do that in Europe, which was not so good in the last half year? But maybe it will change. You know, the stock markets are not so easy to predict. And here are some ideas how to do the analysis with simple autoregressive models, and use also the variances, the volatilities, and we'll talk about this a little bit later, to forecast the variances and derive optimal portfolios. But I guess this will be the topic of one of the next workshops. So that's what we talked yesterday, and I hope Banaglore is successful. It's right in the center of where the money comes, I guess, in the future. So here is the output, and the output is always done in this type of S plus output, where the dollar means this is an output file where you can extract all these components, like beta is the estimate of the coefficient, sigma is the residual variance estimate, and the log ML is the log marginal likelihood, and then the fractional parameter. And that's what you see over here. All the all the modules are listed here, which are available now in the PC version, and ML FRA is just the one over here. You see that here, and then you get other marginal likelihood. See, for instance, the one with the, oh, thank you very much, the one with ML out FRA is the same as the ML FRA, but only with outliers, and then you have the multivariate marginal likelihood, and then you have it for vector auto-regression, multivariate vector auto-regression with fractional prior. So we got this with fractional prior, and this thing which comes in here with inf is the informative prior. So that's not the best idea is always what we start here, and I have done some of these estimates here, and some matrices you get here, marginal likelihood. But let me run this, go down at the end, and now try this one, which is ML FRA, which comes with an implied I think MSCI World Index, and now you see you should get the same numbers as we have over here, 0.006 for the intercept, 0.738 for the all right, the pointer for the beta 1 coefficient of the autoregressive process, which is the same here. And that's the, I think, the OLS estimate here for the fractional prior, then the residual variance, and here the log marginal likelihood, which you can use for testing or model selection. So that's one thing to do. And we have also listed the formulas for the informative priors, as I told you. So if you have multivariate or univariate analysis with informative prior, then you should get another module. And as in the AIC procedure or BSC, as Professor Ghosh mentioned, you can have a P-max argument. So you look for the best order selection over a certain range. So the maximum lag length here. And here you can have a choice of doing it with fractional prior, or you can do it with informative prior. And the informative prior was the type of tightness prior or Litterman prior I have shown to you. So let's see if this MRINF works. Yeah, so this always comes quickly, and you have to be, you go back here, and so this is the informative version of this marginal likelihood. And remember, I told you this is always the ratio of three parts coming, the ratio of determinants, prior and posterior, and one star is always the hyperparameters of the prior, and the double star is the hyperparameter of the posterior, then the gamma function, and the error sum of squares function. And that's what you get here. You get the prior. B star means the prior mean, which is in this autoregressive case 0, and then you have the prior variance, which is usually very large, because it's difficult to come up with some ideas how big this should be. But I have some ideas always how to do it automatically by looking at the variance of the dependent variable, and by thinking how much you can explain in terms of R squared. You can either divide the variance of the dependent variable by 1/2, or then you get about 50% R squared, or by 1/10 you get about 90% of the R squared. So this is the prior, and that's the prior H star. And what you see here is you get this tightness prior, and look here, it's H star I with the coming at the end, and that stands for inverse. So usually the inverse is the precision matrix, and the precision matrix is easier to recognize. So 100 is a relative large variance for the intercept. If you're measuring, we're all measuring here in returns. So this is the automatic prior for returns, and then you have 1, 2, 3, 4, 5, so up to lag, a maximum lag of 5. You have the tightness prior, so it gets the precision gets higher and higher. And for the normal gamma prior, which I told you, their prior degrees of freedom is n dot star, which is 1, the smallest number available. And here already you see the output, which is beta, and the beta is the OLS estimate. Sorry. So what happened here now to the beta? I'm expecting a little bit of a different output. Let's see what is done here. Oh, yeah. See, what you get here is, you see there. Let's start from the back here. The log marginal likelihood for these 5 processes: AR1, AR2, AR3, AR4, AR5. Fortunately, we still will play around and to give you a little bit more of intuition what is going on here. And then you go just, you can either do the testing, the formal Bayes test, and if you think what was the Laplace assumption, all of these 5 models are equally probable, then just taking the ratio of those two or those two or those or whatever, it would give you the Bayes factors, and summing up all of those and dividing by the sum, you would get the posterior probabilities. But for the model selection, as for AIC or BIC, what Professor Ghosh was talking about, you just select the largest one, and you see here the largest one is, fun enough, is the first the AR1 model. So there you get a high penalization by the marginal likelihood. AIC, I think, tends to pick up 2 or 3. And up there you see the residual variances associated with those 5 estimates. And you see they're always getting smaller and smaller. But as this order selection tells you, you make the discount with the degrees of freedom. And here it should be, I don't know, this comes not out correctly now, but those are the coefficients of the AR process. And they should come up as a 5 times or 6 times 5 matrix. You see here the first 2 coefficients are the autoregressive process of order 1, intercept and the regression and the AR1 coefficient, and then you have the 4 zeros because the others are set 0 for the AR1 process. Then you get here the AR2 process, intercept, and AR1, AR2 coefficient, and then the rest is 0. And then you get here the AR4 process. They should come up as a matrix. I don't know what this, so this is always happening with the software if you adjust it so they don't come up as I expected it to be. So that's the idea of this Basel package. I can show you that from their manual. So that's how their matrix, the output matrix should come out: AR1 process, AR2, AR3, AR4, and AR5. So that's the simplest case of order selection for an AR model. And yeah. So let me do some theory, and it should be in the package also, or you can adapt the package pretty soon. Is how to do the unit root test. We discussed the other day about should you use stationary and non-stationary models, and we said, well, from the Bayesian point of view, the asymptotics is not different. You can condition on the data, and the data is very relaxed if what you think if they are stationary or not. But then you can test for that in a Bayesian environment in the following way. This would be the AR1 or ARP process in first differences, and that's what we call here by delta. Take this one, I like this better. That's a nice one. So if you think the time series is integrated of order 1, which is denoted in econometrics by this notation I1, then you can calculate an autoregressive process in the first differences, and CT is now the first differences here. We call this process an autoregressive process in the first differences. So this is the first model. And then we have the so-called simple augmented Dickey-Fuller regression. That's the ADF, which is always called, it's written here in econometrics. And what you do here is you just extend this autoregressive model in first differences by one term, which is the first one here, by regressing it to the levels of the time series. And if this term comes up significantly, or the marginal likelihood in the Bayesian framework is higher for this model than this one, then you pick this model, and that would tell you the process is stationary because you picked the Dickey-Fuller regression model with a significant coefficient. So in classical terms, you always test if this regression coefficient A0 is 0 or not. And then you get some extension of this augmented Dickey-Fuller test that you can have a stationary process with drift, and you test if it's stationary or not by looking at this term. And of course, what the classical people don't know, which order to pick. So they pre-pick any order, like 5 or 8, if you have 2 quarters for 2 years with quarterly datas and so on. And another one is here. With the Dickey-Fuller test with trend and drift, so you have a mu plus beta t plus alpha 0 times the level parameter, and then the autoregressive process. So and for all these models, as I told you, since we condition on the data, the marginal likelihood, for instance, the fractional marginal likelihood stays the same. So you can do a simple unit root testing by just calculating this quantity and find out what is good and what is not good. And as well, you can extend this model by to different complications. One I showed you the last time, it was the breakpoint model. So you think that the whole time series can be broken up into regimes, which is shifting at a certain unknown point of time, which you don't know, and you search for this unknown breakpoint as we search for the order of an autoregressive process. Or you think there's an outlier in the time series present. So what you do, if you don't know where the outlier is, if you know where it is, it's easier. Just plug in a dummy variable, dj, at the time where you expect the outlier, and then you estimate the whole process. But if you don't know that, then you run t outlier models at that time. If you just expect one outlier to be present in the time series at the time, it could be more than 1, 2, and 3. You see that the combinatorial explosion is possible in any type of these search models. And so what you do here, you estimate an autoregressive process with what we call here an additive dummy or additive outlier model. There's innovations and additive outliers. Innovations outliers are a little bit more complicated to compute, but here we do it just for the J model. And then we calculate by the same way the marginal likelihoods by fractional prior or non-informative prior, and find out graphically how to do that. And that should be also part of this Basel package. Well, now I haven't tried this one, but let's see if this works. With their default data set, that should be ML out fraction likelihood. All right, so it's easier if you know all this stuff. Then it's easier to do. So you get even here, you get the time series output. Here are the first differences, and here are the marginal likelihoods. Yeah, probably you can make this larger. If it's large enough, is this large enough or not? All right, so you see here, then the time series, and associated down here is this quantity here, the marginal likelihood calculated, and you see where the spikes came up. You can't see here, unfortunately, the scale of what it is. But everywhere where you see a spike, this is a possible location of an outlier. So it was here, and then here again. So you see a graphical display, and you can do that by looking at the figures of the time series as well, of the marginal likelihoods, and do that. So let me show an example where I applied this idea of outlier testing. And then you see you can combine it with any complication of the model. So this is from a paper which you can download from the web, which I like to be put in the conference handout what you have seen, and because the paper you have now in your is actually the paper following this idea, because I generalized the so-called tile decomposition if you do forecasting of the stock indices, for instance, and we want to find out is it reasonable to forecast with arch models, which I haven't shown you what it is, but it's also forecasting the variances. You think the variances are time varying as the means in such a time series model, or should you stick with a constant model? What is better to do? And there's little about this in the literature, from a classical point of view, you started doing this by having some ideas of interval forecasts. And I did in one of this extension interaction of the channel style decomposition, and showing how you can, for a multivariate model, use the univariate tile decomposition and do it. And then for the Bayesian type of stuff, do their evaluation of the forecast performance by looking at the predictive ordinates. So the idea is a better prediction has a higher ordinate under the predictive density than a not so good prediction. That's basically the idea of the paper you have in your notes. And here is the way we estimated that. So we did this during the so-called Asia crisis, and that's also a nice topic to mention here, because everybody talks about the Asia crisis, and if you ask different people, you get different answers. When has the Asia crisis occurred? And see if you apply, and this paper can be downloaded, as you have seen here on the website. So those are the three time series we're looking at, and we also using for this capitalistic pricing model what you have seen before. That's the Nikkei index, that's the DAX index, and there's the Dow Jones. Actually, this is the special case of what you have as a data set, the default data set in the Basel package. This is because we have the MSCI as an index of the three continents, and here we've just picked the most important countries in the three continents, the Dow Jones, DAX, and the Nikkei. And you see this is daily data for the last 2 years. And actually ending in 98 now, already. Time is running fast, unfortunately. And then you see here the first difference, and you see that so-called volatility clustering. So you have certain points in time where the variances tend to be larger than in other ones. And we wanted to find out, was there a break or an outlier, it's just an outlier break in the middle of 97, which is the year where the Asia crisis started, and it started, in Thailand, and we went to Indonesia, and then affected other countries. I think India was not affected as much as the rest of Southeast Asia. And then if you apply our outlier detection procedure, which I just showed you over there, then we want to find out what is the date. Where did the outliers occur, and did it happen at the same time? And funny enough, now you see, for the first is the Nikkei index. Nikkei really started out to be the last one in this three series to be affected by the Asia crisis. The first one was on October 23rd. It was everything comes out of the Dow Jones of the New York. The New York Stock Exchange was really hit hard on this October 23rd, and not in the summer, when in the summer where they started all the problems with Thailand and Indonesia, and they accused people speculating against it. So that might have affected trade orders and so on, but not the stock market. The stock market was affected much later. And see, then on the next day, the DAX, the Germans were affected. They always look what is going on in the US. If somebody coughs there, then it has really some effect. But the Japanese, they waited about 2 or 3 weeks, and only in November, and here the November 13th, they had the highest loss, highest drop in their stock Nikkei index, which started their downturn of the Asia crisis. So that came as a surprise, and this is just an extension of what I showed you with the margin likelihood, what you can do. And here is the picture how the Nikkei was as index over in those 2 years, from 96 to June 96 to June 98, and the Asia crisis was just in the middle. And so the Nikkei really went down. I think now it's going up, and DAX went up, and the Dow Jones went up, except for this period where this Asia crisis happened, where you had a sideward movement, as it's called, in the stock index. So That's so far for the stock index. So to find out if this series are stationary or not, should you do that in first differences or in the original time series? So you look at the data and again at the marginal likelihoods. And here are the four models I just showed to you by testing their stationarity of the model. So these are original data. Delta AR is the model in first differences. And then you have Dickey-Fuller test with an autoregressive order up to order 3. And then you have the Dickey-Fuller with a mean and the Dickey-Fuller with mean and trend. I haven't put in here the outliers, so this is not done here. But you have here the three indexes, the Japanese, DAX, and the Dow Jones. And you see if you take their original stock index, so the original series, they are all non-stationary. Why they are non-stationary? Because the model in first differences gives the highest marginal likelihood, and 3633, so it's much larger than 3645 for this one. And the order you pick at the same time, it's the order 1 here, order 1 here as well. So, and all three series are clearly non-stationary if you follow this simple test what I put out. And if you do the same test now for the first differences, then you see the non-stationary model is never picked. The 2 stars is always the maximum across all these numbers here. And the nice thing about this marginal likelihoods is you just compare them all together. And if you say, well, I would like here a breakpoint or an outlier or a time-varying model, you just plug it in and calculate. It's an only question if you have a software system flexible enough to do all that in decent time. So here you see they are stationary with this outer trend. This the DAX is stationary with a trend. So some people suggested making money off of that if you know what the trend constant was in those 2 years. And see the Dow Jones is again stationary without a mean, and yeah, with a mean here. And the order is always picked to be order 1 in all these cases. So. Just to get you an idea what you can do now, not so far, if you don't believe it, so far everything has been simple. This is simple linear Bayesian modeling with conjugate priors. Nothing happens. There's normal distribution, still assume no t distribution, no other thing. Well, what we did, we extended it to t or hyperbolic distribution, find out what the loss could be. If you could do a little bit of non-parametrics, but still it is non-parametrics in time series. This is from a Bayesian point of view is an adventure to a certain extent. But here are some ideas what you could do for a multivariate model. So that's what we call an arch model, arch in-mean model, arch PQ model, and feedback of their volatilities to the mean equation, to the returns. And that's what we call arch-mean model. And the idea is that given us the information data set, so all the realization of the time series up to point t, that the observations are normal, multivariate normal. So I put here the blue stuff beyond it is designed that they are all vectors, and HT is now the time-varying covariance matrix. And what you do now here is you relate the means of this distribution here to the past of your own time series and the past of the other time series. And here the psi variables are the feedbacks now, which relates to the arch-mean model. So how are the volatilities having effect on the returns of the time series? For instance, if you look at now our our stock indices. And then this is only one way of modeling, and then you can do the same thing for this covariance matrix here. So you take the covariance matrix, vectorize it, so vec H means vec half. You take only the half of the matrix because it's the same positive definite covariance matrix, and each element of this matrix can now be an autoregressive process as well. So the order P relates to their own paths, this is this, and Q to the squared errors of this time series here, where ut is the deviation yt minus mu t of this equation here. So this shows you how complicated this whole stuff can get, and this is RLK, so if you extend that even more, make it more complicated, you have anything you want to make it complicated. So this is the models we are now really dealing with a multivariate setup. And then the question comes up, can you estimate them and can you do the model selection? No. And the answer is yes, you can do it, but unfortunately not as easy as the formulas I showed you who were responsible to calculate this. You need Gibbs sampling or metropolis steps within Gibbs, what is usually called MCMC algorithm in all these models. And we used the method of CHIP to calculate the marginal likelihoods to do their model selection. So SID-CHIP has developed now new techniques, and first the published version of 95 in JASA is so-called simple version, still complicated enough if you do all this calculation in a multivariate setup like this. And now he has a new one to deal with exact marginal likelihoods if you are using metropolis Hastings steps in your estimation. And that's the reason why you find in my paper two alternatives how to calculate marginal likelihoods. Well, it would be interesting if this relates to the model selection, which Professor Ghosh just talked about it, or the multivariate setup. So here is the posterior marginal likelihood, which is a concept which was developed by Atkinson, you see that, and published in the Journal of Royal Statistical Society B. And the idea is not to use the prior information for integration, but using the posterior distribution for integration. And this is usually heavily disputed, because then you're using the likelihood twice, once for the estimation and then for getting the integral done. But what we did here was we used the so-called partial posterior marginal likelihood. We integrated out the autoregressive part, because this you can do in closed form, but not the variance part. So for the variance part, we stick with the posterior sample, and then we do the order selection. And you see here the star points out the order which is the best of all these models. So K is the order of the autoregressive process, R is the order of the Arch-E mean equation, that's here, and then PQ is the order of the Garch equation. For all this, for now this three-dimensional system of the Nikkei index, of DAX and Dow Jones. And here is the order selection by posterior marginal likelihood, and here's the order selection by pseudo-marginal likelihood. The pseudo-marginal likelihood is something like a cross-validation, which was briefly mentioned as well, and you do it for the time series very easily, so you always calculate the next for the next observation the predictive density, and then you plug in the observation you got, and doing all this it gives you then a marginal likelihood which is called predictive marginal likelihood by Geisser and Gelfand and Day, another famous Indian working in this area. And funny enough, they always give for our problems, well, so we have a few hundred observations here, about 600, the same order selection. And then now in the new output you see the exact calculation of the marginal likelihood, which gives you also the same order what we are doing here, the order condition. So. And just to show you the mere huge of data output, what you get, here's the three-dimensional system, Nikkei, DAX, Dow Jones. We have now summarized the posterior distribution, which is huge. I don't know how many parameters there are, about 30 and more for each equations. the posterior posterior estimates, which are larger than one standard deviation, are put out in bold. So you see how difficult it is to get some idea what is going on. But what you get a quick glimpse is here that the autoregressive part, so the mean equation part, which goes up to here, is more sparse than the volatility part. So it seems that the volatility interaction between the three stock markets, the continental model as I call it, is very rich, while it's not so for the autoregressive part. And this makes sense from the economic theory, where you think that the stock markets are more or less efficient. Efficient means that the returns from other markets should not influence the returns of your own market too much. So that's what we did here for this three-dimensional system. And just to tell you how complicated things can get, we did this also for the Asia crisis, where we thought now that the Asia crisis is where the stock market will hit by the Dow Jones index, so the 23rd of October, and we estimated that before and after. And that's a simple test of structural break. Is the system the same before the Asia crisis or not the Asia crisis? And that's what we can test as well by just calculating the marginal likelihood for these two models. And that's what we did. And I think I have to stop pretty soon. So I show you the outcome of this analysis. So here is a simplified version of the estimation output, where what I just showed you by the big columns of means and standard deviation of the posterior distribution. And to explain you a little bit what is going on here is there is Nikkei, DAX, and Dow Jones. And here you have the autoregressive part of the time series, and you have here their autoregressive mean part. So that's the feedback of the volatilities on the system. And we want to find out some kind of structure. So it's some type of graphical models, but it's not a simple version, just making sense of all the coefficients. And what you see is that the Dow Jones gets, so the black arrows are positive influences, where the posterior T values are larger than 1. And the dotted areas are where the posterior T's are negative. So you see the Dow Jones gets lots of influence from Nikkei and DAX in his own past. But what is also interesting that the volatilities are heavily making feedbacks to Dow Jones, to Nikkei, and the DAX. So all of those time series seem to be very interlinked. And we were quite surprised by this result. So what we did is we did the same thing for the exchange rates. So then we said, well, this is the pattern, but what we see in the stock market also present in the exchange rate market. So we had the US dollar, US yen, and the D-Mark yen relationship. And you see here as well feedbacks coming from their own past. So it's a little bit of non-inefficiency and feedbacks coming from the volatilities. And finally, we did a test and the test which is done by so we tested the structural breaks by marginal likelihoods. See, all the stuff what I showed you from the simple models up now to the complicated one is, can you do complicated tests? Can you now test if the Asia crisis was present for the stock returns models for the three-dimensional, or the exchange rate model, and so on? And now we had the two periods from June 96 to June 98, about the 2 years period roughly, and we had the two sub-periods where we picked out the October 23rd by this outlier procedure which I showed you just before, and we estimated this model. So here it was this partial marginal likelihood by posterior distribution, but we can do that now. That was our latest addition to the package by the exact marginal likelihood method. So here you see the stock return model. So you calculate the marginal likelihood for the stock returns, and the numbers here in parentheses are the order of the models. So you see the order of the models change quite a bit if you go across different subsections, different stock returns or exchange rates, and so on. So that's the first period before the October 23rd. That's the second period, and that's the sum of those two to marginal likelihood. And here you can see the marginal likelihood for the both of the periods. So that's exactly the way AIC or BIC would do it if you follow archaic type modeling in the old type of Timsark models, if you have ever seen that, what he developed. So you see here that the sum of those two models for the stock return is -2.4, so it's much larger than estimating the whole the model for the whole period, which is 2,700. So the base factor, if you think that both models are equally likely, would certainly favor the breakpoint model and not the overall model for the whole period. Now let's see if this also holds for the exchange rate. So the exchange rate has a sum of the two models, which is 3,233, and it's 3,011 here. So you see the exchange rate model doesn't support the Asia crisis, which is interesting. You see it in the stock market, but not in the Asia crisis. This is the period 3.1 is larger than the sum of these two. And now you can do the 6-dimensional model, which we did over here. So this is the maximum we can even get out of our model there at that time. And I'm not sure that the PC version is always working properly for that. So you see the stock exchange model, it gives you the same answer, that the joint model is better than the breakpoint model. So if you really look for a structural break, you only see it in the stock returns, but not in the exchange rate markets, and not in the stock return, in the combined model with stock exchange and exchange rate at the same time. I think I will stop here, and I've given now a little bit of outline what is going on and could be done in future, and I think we can report much more on Bayesian practical econometrics and modeling in future, and I hope you can also use our system, and thanks for your patience. I'm willing to take some questions for in the afternoon.
This is a very impressive system. I hope you send me a copy.
Yeah.
When you do marginal likelihoods or posterior odds on model 1 versus model 2,
right,
and you find the odds for model 1.
Right.
George Box many years ago made the point the odds may favor one versus the other, but both of the models could be terrible.
Right.
So have you checked out these models and forecasting the stock prices?
Well, yeah, to say, yes, we did the forecasting. So the idea is, well, one idea is, and one good American idea is always, can you make money out of that? Can you speculate now on the stock market? And then you have to use all these models here and do the forecasting and find out if you plug it in a special model for investing. Now we see we have 3 regions here, 3 continents. Should you invest more in Europe or in Asia? And this type of model should give you the right answer. So that's what we're doing now. We use now the forecast, at least the one, well, it's a little bit more, you see what complication comes in. This is daily model, and if you don't want to speculate every day on the stock market, it gives you a lot of costs. But the as I said, this is a daily model, and the daily models are not used in brokers for doing this type of portfolio decisions. So they're using a monthly model. So now the issue of aggregation comes in. So we did a similar analysis for monthly models, and only for not for this period, now for the last, I think, 18 months. so up to December 99 now. And we did this simple, which is a toy model for brokers as well, because but it would give some global outlook. And we did the forecast with this Archie mean model, and we could show that we are beating now the MSCI World Index by a margin from about 1% point. So you can do that by using this VAR mean model for now for the last 18 months. But still, to convince people to put money on this model, we have to do a benchmark longer. Yeah, of course, you never know if that's the true model or not. So there are certain things open, how to extend the model, like the time-varying model, which is not built in here. Or is the distribution correct? Should you use the t-distribution instead, or another one? Or should you use other variables, a leading indicator variable? So there's still lots to do. But that's the reason why we put up the system and try to do that.